Have you ever really stopped to think about how our modern world is, well, made? All the plastics, the medicines, the fuels around us. It turns out our world isn't so much built as it is cooked. Yep, almost every synthetic material you can think of started with a recipe, a super precise set of instructions to turn simple stuff into something completely new.
And this right here is one of the cookbooks. It's called the Chemical Process and Design Handbook. Now I know, it looks like some ridiculously dense textbook, but I want you to try and think of it as maybe the most important cookbook you've never actually read. Okay, let's dive into this.
Because inside, you're not going to find recipes for food, but for literally everything else. The book is actually split into two parts, which is pretty clever. Part 1 covers all the fundamental cooking techniques, and Part 2, well, that's where you find the specific recipes for thousands of different chemicals. It's basically the ultimate guide to making, well, just about everything.
So in this explainer, that's exactly what we're going to do. We're going to take a little peek inside this chemical cookbook, get a feel for the basic techniques, and then we're going to follow one simple recipe just to see how the world we live in is literally manufactured into existence.
All right, first up, let's look at the basic skills that every chemical chef needs to get down. These are the core processes from Part 1 of the handbook, the kind of things that get used again and again and again in all sorts of different recipes.
So the first technique is polymerization. The easiest way to think about it is like this. Imagine you have a huge pile of individual paper clips. Those are our monomers, and you start linking them together one by one to make a long, strong chain. Well, that chain, that's the polymer. It's the basis for pretty much all plastics.
Now check this out. This is what that whole process looks like written down in the cookbook. This is the recipe for polyethylene, the most common plastic on Earth. On the left, you've got n number of ethylene molecules. That's our pile of paper clips. And on the right, boom, they're all linked up in a long chain. It's simple, it's elegant, and it's incredibly powerful.
Okay, another absolutely essential technique is oxidation. On a really basic level, you can just think of it as a very, very controlled and precise kind of burning. It's one of the most fundamental ways to transform one chemical into a totally different one. But, and the handbook makes this super clear, the absolute key is control. Think about it. When you burn a log in a fire, you're just oxidizing it all the way down to ash and smoke. But in industrial chemistry, the whole game is to stop that reaction at just the right moment to create a specific, useful, new thing. It's kind of like the difference between burning your toast to a black crisp and getting it perfectly golden brown.
So now that we've got our basic techniques, let's actually put them to use. We're going to follow a specific recipe from Part 2 of the handbook for a chemical called acetaldehyde. It's a really key ingredient for making other things, like acetic acid, resins, and dyes.
And this is our recipe card. It's a flowchart that shows the entire process for making acetaldehyde using that oxidation technique we just talked about. I know, it looks a little complicated, but it really just boils down to 3 main steps: reacting, scrubbing, and distilling. Let's walk through it.
Step 1 happens right here, inside the reactor. This is our main cooking pot. This is where we feed in our primary ingredients, in this case, ethylene gas and oxygen, along with something called a catalyst, which is kind of like a chemical spice that just helps the whole reaction happen way more efficiently.
The next few steps are all about purification. The hot gas that comes out of the reactor is first scrubbed with water to cool it down and capture the stuff we want. Then, that whole solution goes through a distillation process, which is kind of like reducing a sauce to separate out the pure acetaldehyde from everything else.
And what do we do with this stuff we just made? Well, we use it as a building block for an incredible range of other things. Acetic acid, which is vital for making plastics and fibers, resins for manufacturing, dyes for our clothes, preservatives, and even the chemicals used for silvering mirrors. It's a perfect example of how one simple recipe becomes the starting point for dozens more.
So we've followed a recipe, but the environment where this cooking actually happens is a world away from your kitchen at home. Let's take a look inside the industrial kitchen.
So what really is the difference between a kitchen oven and a chemical reactor? Well, besides being absolutely gigantic, it really comes down to 2 things: temperature and pressure.
I mean, just look at this comparison. Your oven at home might hit, 400 degrees Fahrenheit at normal atmospheric pressure? But some of these industrial recipes, we're talking about temperatures up to 400 degrees Celsius and pressures of 290 pounds per square inch. That's nearly 20 times normal air pressure. It's those extreme conditions that force molecules to break apart and then recombine in totally new ways.
And, obviously, you can't use a Pyrex dish for this kind of work.
The handbook describes the cookware of this industrial kitchen as these massive vessels made of cast iron, stainless steel, and even some exotic alloys, all of them engineered to handle this intense heat, the crushing pressure, and super corrosive chemicals without failing.
All right, so now that we've seen the kitchen and we've followed a recipe, let's zoom back out and take a look at the full menu that's on offer in this incredible cookbook.
This is just one single page from the table of contents. The list of recipes goes on for pages and pages, covering hundreds and hundreds of chemicals, all listed alphabetically from acetaminophen all the way down to zinc sulfide. It truly is the menu of modernity.
And you know, hidden among all those complex chemical names, you'll find plenty of things you recognize. The recipes for aspirin and caffeine, they're in here. So are the instructions for making detergents, glass, nylon, paint, and soap. These aren't just abstract ideas. They are the literal ingredients of our daily lives. The author, James G. Speight, really just puts it perfectly right in the preface. He says, chemicals are part of our everyday lives. They influence what we do and how we do it. This handbook isn't just a collection of processes. It's really a blueprint for the world we've all built.
So, the next time you pick up your phone or drink from a plastic bottle, just remember, it didn't just appear out of nowhere. It was designed, engineered, and cooked from a recipe in a giant industrial kitchen. Which kind of makes you wonder, what recipe in the world around you will you see differently now?